Hello, viewers. In today's class, we are going to discuss an important integral with the help of Laplace transforms, right? So, viewers, we know that Laplace transform is a powerful tool in evaluating important integrals. So, in this session, we'll see the method how to evaluate some important kind of integrals using the Laplace transforms, right? So let us start. So here we have to evaluate this integral that is from 0 to infinity, and the integrand is cos t minus cos 2t over t and dt, right? So what we will do here, let us first take this integral as I, right? Now, see, this integrand is of this form, that is f of t divided by t, right? So here we have t, and the function cos of t minus cos of 2t can be taken as f of t, right? So we have cos t minus cos of 2t divided by t, right? So we'll assume f of t as cos of t minus cos of 2t, right? And then we'll find out the Laplace transform of this function f of t. So the Laplace transform of f of t is L of f of t, and then we have L of cos of t minus cos of 2t. And now by the linearity property of Laplace transforms of two functions associated with negative sign, we have L of cos of t, then we can write L of cos of 2t, right? So now let us apply the result, that is the Laplace transform of cos at is given by s divided by s square plus a square, right? So in the first case we have cos t, so cos t can be written as cos of 1 times t, so the value of a is equal to 1, right? So the Laplace transform of cos t is s over s square plus 1 square, and in case of cos of 2t, the value of a is 2, right? So here we have s over s square plus a square is 2 square, right? So we can now write s over s square plus 1 minus s over s square plus 4, right? So the first step to find out the Laplace transform of f of t, which is this expression. So now we know that the Laplace transform of f of t is denoted by f of s, right? So L of f of t is equal to f of s, right? So the first step to get this expression, right? Now let us replace this s by the variable x, right? So that we have a function f of x that is equal to x divided by x square plus 1 minus x over x square plus 4, right? So the second step is to replace this s by some new variable x and to get a function f of x. So now we use an important property of Laplace transform involving the integrals, and the property goes like this, that is the integral of f of t divided by t from 0 to infinity is equal to the integral 0 to infinity f of x dx, right? So this is a very important property while evaluating integrals of this kind. So here we are using this property and we are not going to derive this property, but here we can mention that this property can be obtained from an important result, and the result is that the Laplace transform of f of t divided by t is equal to the integral s to infinity f of s ds, right? So this is another important property of Laplace transform, right? And this property says that the Laplace transform of some function f of t divided by t is equal to this integral, that is from s to infinity f of s ds, right? And from this property we can derive this property, right? But here we will directly use this one. So now let us substitute the values here in this result. So we have 0 to infinity. F of t is our function cos of t minus cos of 2t divided by t, and here we have dt, right? And this should be equal to 0 to infinity, and we have f of x dx, and f of x is x over x square plus 1 minus x over x square plus 4, and here we have dx, right? So this side, that is the left hand side, is equal to our integral I, right? And we have to now evaluate this integral. So now I can be written as the sum of two integrals or the difference of two integrals. So we have 0 to infinity x dx divided by x square plus 1 minus 0 to infinity x dx divided by x square plus 4, right? Now what we can do here, we can multiply the numerator by 2, and here we'll write 1 over 2, right? So that 2 and 2 get cancelled, and similar is the case with this one. Here we will write 2 and we'll write 1 over 2. So why we are writing? Because the derivative of x square plus 1 is equal to 2x, right? And the derivative of x square plus 4 is equal to 2x, right? Because from indefinite integrals we know that the integral of f prime of x over f of x dx is equal to log of f of x, right? So here we have now a half, and we have log of x square plus 1. F of x can be written as x square plus 1. So we have f prime of x as 2x, right? And similar is the case with this one. So we have 1 over 2, and here we have log of x square plus 4, right? And we can take the limit with entirely on this entire term, that is 0 to infinity, right? So we are not separately writing the limits, so we'll combine these two terms and we'll write the limits 0 to infinity, right? Now here we can take half common, so we have log of x square plus 1 minus log of x square plus 4, and the limits are from 0 to infinity. Now applying the properties of logarithms, this is log m minus log n, that is equal to log m over n, right? So we have log of x square plus 1 divided by x square plus 4, and the limits are from 0 to infinity. So now to evaluate this term, first we have to take x tending to infinity, right? And then we have to take x is equal to 0. So what we will do, we'll write half, and then we can write limit x tends to infinity, because here we cannot directly substitute x is equal to infinity, right? So we'll make use of the notation of limits. So limit x tends to infinity, we have log of x square plus 1 over x square plus 4, and then we have minus sign here. Then we'll take x is equal to 0, right? So when we take x is equal to 0, then this term and this term becomes 0. So we are left with a log of 0 plus 1 over 0 plus 4, right? Okay, so now we have to evaluate this limit. So what we will do, we'll write half, then limit x tends to infinity, and we can write log, and here we can divide the numerator and denominator by x square. So we can have 1 plus 1 over x square, and here we have 1 plus 4 over x square, right? And here we have log 1 over 4, which can be written as 4 raised to minus 1. So now when x tends to infinity, it implies that 1 over x square, it tends to 0, right? And similar is the case with 4 over x square. So 4 over x square also tends to 0, right? So when x tends to infinity, then 1 over x square and 4 over x square tends to 0. So now we can write half, and here we have log of 1 plus 0 divided by 1 plus 0, and here we have plus log of 4, right? So applying the properties of log, that is log m raised to n is n log m, right? So now this term is log of 1. So we have log of 1 is equal to 0, right? So we have half, and here we have log of 1 plus 0 is 1, 1 plus 0 is 1. So 1 over 1 is 1. And here we have log of 2 square, right? 4 can be written as 2 square. So we have half, log of 1 is 0. And here we have 2 log 2, utilizing this property log of m raised to n is n log m. So now this can be written as half times 2 log 2, and 2 and 2 get cancelled, and we are left with log of 2, which can also be written as the natural log of 2, right? So viewers, the value of this integral is equal to the natural log of 2. And this is how, by making use of the concept of the properties of Laplace transform, we can evaluate these type of integrals.